In this video, I want to show you how I can automatically run the simulation that I've described in the previous video using the choice function. So at some point in my program, I have to say from numpy.random import choice, and now I get to use this choice function. So here's what I can do. I can define the possible choices and the probabilities for each of those choices. So for example, if my possible choices are pass to the left, keep, or pass to the right, and my probabilities are 0.15 for left, 0.7 for keep, 0.15 for right, then this is how I would set things up. Let me read this in. And now I can define the number of kids to be, for example, 8. And now I can get the choices that each of the kids makes. So here's how it would go. So it's a choice, and then the first argument is going to be possible choices. The second argument is going to be the number of kids, and the last argument is going to be the probabilities. So if I now run that, what I get is, and if I convert this to a list, what I'll get is a list of 8 choices that were made according to those probabilities. So I can of course vary the number of kids, and I can have fewer choices. And I can run this again and again, and I would get different choices every time. So that's perfect for my simulation. So let me copy this, like so. So now let's say that what I want to do is I want to write a function which I'll call getTurn differences, like so. And what it'll take is it'll take the number of candy bars that each of the kids has, and also the number of kids. So to clarify, for example, counts might be something like 10, so the first kid has 10 candy bars, and then the second kid has 2 candy bars, and then the third kid has none, and then the fourth kid has 10 as well. So that would be one possibility. And kids in this case would have to be the length of counts, which would be 4. So what I want to do is I want to take the counts currently and the number of kids, and what I want to return is I want to return the difference that needs to be made for each count. So for example, the differences might be something like -1, +1, +1, and -1. So you can figure out which choices need to be made in order for those differences to be the correct differences. So then at the next turn, what will happen is that this count would be 10 minus 1, so 9, and this count would be 2 plus 1, so 3, this would be 1, and this would be 9, for example. So this is what I want to do, and I want to make this basically random. So let me write this function. So it's still going to be the case that the possible choices here are left and keep and right. And now the probabilities are like that, and I can now make the choices. So I can say choices is equal to this. So now I get a choice for each of the kids. Now, if you remember, we have a bit of a problem because this kid, they have 10 candy bars. They cannot pass their candy bar to the left. This kid cannot pass their candy bar to the right. So let's just take care of this before we compute the differences. So what we'll say is if choice is 0, so if the choice of the leftmost kid is to pass a candy bar to the left, well, we'll just modify it, and we'll say that really what they mean is that they want to keep the candy because there is no way to pass the candy bar to the left. In the same way, if the last choice, so if the choice of the rightmost kid is to pass to the right, we'll just say choices at -1 is equal to keep. So that fixes that problem. We still have the problem of, for example, this kid deciding to pass a candy bar they don't have, let's say, to the right. So in order to take care of that, we actually need to loop through all the choices. Choices would look kind of like this, and make sure that this doesn't happen. The last thing that needs to be done before we actually go through each of the choices and see how they affect the counts is that we need to actually set up the thing that we're going to be returning, which is the differences. So the differences initially should be all zeros. So we can set it up like that. So we can say differences is equal to 0 times n kids. So right now we set n kids to be 4, so 0 times n kids would be this. So we're just setting up this list, and we're going to keep updating it as we go through the choices and see how they affect the differences. So let's do that. So I need to go through each of the choices, and the way I'll do it is like so. So I'll say for I in range the length of choices. Why don't I go for choice in choices? So why don't I do something like this? So on its face, it kind of seems reasonable to do this, except remember, if, for example, if for example, this kid decides to pass a candy bar to the right, that means that the difference in this position needs to be -1 due to this, but the difference in this position should be +1. And the only way to affect the neighboring differences is to know the index. So that's why I am deciding to go with for I in range length of choices. So, okay, here's what I'm going to do. I'm going to say, okay, so if the choice is keep, then that shouldn't matter. If the choice is right, and if also the counts at I are not 0, which means if I get to pass anything at all to the right, then how should that affect the differences? Well, if I'm passing to the right, that means that, first of all, the current kid should lose 1 candy bar, so that should be like that. So I'm subtracting 1 from differences at I, so if it was 0 in the beginning, then it would be -1 at this point. And I should also say diffs I plus 1 plus equals 1. So I'm giving a candy bar to the kid to the right. And I made sure that there is a candy bar to give here. I can do the same thing with the left. So that's going to be like that. And now I'm done. I can return the differences. Let me try and run this. So let me set up counts as, let's say, 10 to 0, 4. So n kids is going to be the length of counts. And let me call get turn differences with counts and n kids. Here's what I get. This is one example. So at this point, I would have to add 0 to 10. I would have to subtract 1 from 2. I would have to add 2 to 0. And I would have to subtract 1 from 4. Those are the choices that were made. Not the only possible choices. So if I call this function again, it would be like that. If I call this function again, it would be like that, like that, like that, and so on. So when I'm doing the simulation, what I'll do is I'll repeatedly call this function. So okay, so I need to actually use those differences. So let me write a function that would do that. I'll call it addDiffs, and it will take the counts and the differences. And all that needs to be done is to just add the corresponding counts and differences. So that's going to be like that. So I'll add diffs I to counts I. So at this point, it's worth thinking about why didn't I just do this directly over here instead of computing the differences and then calling addDiffs in order to add those differences in. Well, the reason is that I don't want to be worried about the situation that's described in the previous video, where, for example, you start out with this kind of situation, and then this kid gives a candy bar to this kid, and then this kid will have a candy bar to give to this kid, which they don't. We said they're all passing the candy bars simultaneously. This avoids this problem, so in this function, I take care to not pass any candy bars if currently the counts are equal to 0. So that is why I have getTurnDifs and I have addDifs. So now we are ready to write the function that will execute an entire turn. So I'll call it runTurn, and it'll take the counts and the number of kids. And what I'll do is I'll compute the differences, which are decided on randomly. So I'll say getTurnDifferences, and this is going to be counts, and this is going to be nkids. And what I'll do now, so this does not affect the counts. This computes a new list, diffs. And what I want to do now is I want to add the diffs. So this is going to be counts, and this is going to be diffs. Okay. At this point, I'm actually ready to run a simulation or an experiment. So here's one idea. Let's start with this kind of thing, those kinds of counts. And what I'll do now is I'll just try to run this a couple times. So I started with those counts. So runTurn, it does multiply counts. So what I'll do is I'll say runTurn counts, length of counts for nkids. And now I can see what counts are. So it's like that. Let me do it like this. So now the counts are like that. So okay, so that's basically how things go. So let's say that they wonder what would happen if I repeated this a lot of times. So what I might expect is that this number will actually go down with time because this kid can only pass to the right but not to the left. And admittedly, this kid can pass the candy bars back, but still I expect that this number should go down. So let's try it. So I'll define nkids to be the length of counts. And let me run this for a lot of times. So let's say this many. And what I want to do is I want to say runTurn counts nkids. So let me run this. This might take a little bit of time. Okay, so that took about a minute, and now I can see what the counts are. And as you can see, yes indeed, this is way lower, so this is now 362, and this kid has 113. So that's kind of cool.